we've applied spectral theory in the context of similar matrices and now diagonal matrices. Now let's do the same thing for symmetric and skew symmetric matrices. So let's recall the definitions here. So A is symmetric if, well, A is equal to its transpose. If you write A as coordinates aij, what this means is aij equals aji for all ij, right? So if you reflect the entries along the diagonal, you get the same thing. For a skew symmetric matrix, you get the negative, right? So skew symmetric. So let's say B is skew symmetric if B is equal to the negative of its transpose, right? i.e., if you had Bij, then that would be equal to negative Bji for all ij. And in particular, what does this mean? Well, along the diagonal, you have I is equal to j. And then how do you have something that's equal to the negative of itself? Well, that only happens when the number is 0, right? So this means Bii is equal to 0 for all I. So a skew symmetric matrix is 0, 0, 0, blah, 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 0. And then you have a bunch of entries over here. And then if you flip it, right, or if you look at the corresponding reflection along the diagonal, you have negative. So like, you know, if you had, so here's Bij, you reflect, you get negative Bji. Cool. So now that we've recalled the definitions, let's understand what we can interpret using eigenvalues and eigenvectors in the context of symmetric matrices. So here's a theorem. We have if A is a real valued, right? And so I'll just say real. This just means Aij is an element of the reals for all ij, right? Real symmetric matrix. Then the eigenvalues of A are distinct. And also, we have that the eigenvectors are orthogonal. So remember, for two vectors or a set of vectors to be orthogonal, it means that they're perpendicular geometrically, but algebraically, it means, so let's say, you know, maybe we have like u1 through un, this set is orthogonal if ui dot uj is equal to 0 unless I equals j, right? This is what it means for a set of vectors to be orthogonal. It means they're all perpendicular, right? And then you'll remember orthonormal just is an orthogonal set, but when I equals j, the dot product of itself or with itself is just 1, right? We have a similar theorem for skew symmetric matrices. We have if A is real and skew symmetric, this implies that the eigenvalues are 0 or purely imaginary. I.e., you know, if you have an eigenvalue lambda, well, this is equal to 0 or lambda is an element of IR, right? Purely imaginary means, you know, when you look in the complex plane, we understand the axes where the horizontal is the real component and the vertical axis is the imaginary component. Well, the imaginary component here is isomorphic to IR, right? Because what this means, well, for a given complex number, in general, it's of the form a plus bi, but to be purely imaginary means I equals 0, right? Okay, Next, well, let's do some examples here, applying these theorems or verifying these theorems in certain cases. Let's look at the symmetric case first. We have A is the 2 by 2 matrix 1, 2, 2, 3. You can verify this is symmetric pretty easily. Well, let's see that we have distinct, and I should have said here in the first theorem, they're distinct and real, i.e. lambda is an element of R. So sorry, I forgot this small result. So let's verify that they're distinct and real, right? Well, to find the eigenvalues, we find the roots of the characteristic polynomial, which is the determinant of lambda I minus A equal to 0. This is the determinant of lambda minus 1, lambda minus 3, and then -2, -2 equals 0. You can see pretty quickly that you will get the characteristic polynomial is lambda squared minus 4 lambda minus 1 equals 0. This implies lambda is equal to 2 plus or minus root 5, right? Those are two distinct eigenvalues, both real valued, right? And an exercise that would be good is to show x1 and x2 are orthogonal, right? That was also a result of this theorem, is that the eigenvectors corresponding to these eigenvalues are orthogonal, i.e. what you would want to do is show x1 dot x2 equals 0, right? Let's look at an example for the skew symmetric setting. Let's let A be the matrix 0, 0, -1, 1, right? Well, we need to do the same thing. We need to set up the characteristic polynomial, which is the determinant of lambda I minus A equals 0, which is the determinant of lambda, lambda, and then 1, -1 equals 0. You can see taking the determinant, you'll get lambda squared plus 1 equals 0, which implies lambda is plus or minus I, which are purely imaginary, right? All right, so now what we want to do is we want to study spectral theory applied to orthogonal matrices, right? Orthogonality is showing up here, but now we want to figure out how to find eigenvalues and eigenvectors of orthogonal matrices themselves. So let's try to study spectral theory for orthogonal matrices. And I'll start with a theorem. If we have a matrix A, which is real and symmetric, then there exists an orthogonal matrix U such that it is orthogonally similar, right? We don't really say that, but that's kind of the informal, intuitive way of understanding what's going on here, to a diagonal matrix D such that we have D is equal to U transpose A U, right? And if you'll recall, for orthogonal matrices, if U is orthogonal, that implies that U inverse is equal to its transpose. So this is very similar to the notion of matrix similarity. And here we know that if a matrix A, right, because if in the case when U is orthogonal, then U transpose is equal to its inverse. Well, that means this orthogonal matrix satisfies the similarity criteria. So we have that A is similar to D. And if you remember, for a matrix A that's diagonalizable, we have that D is the entries are the eigenvalues along the diagonal and then 0 everywhere else. A corollary or result of this theorem is for all A that are real and symmetric, there exists a collection of vectors, say u1 through un. Well, I better include u2. They used to be a good band. And so what this corollary is saying is for all real symmetric matrices A, there exists a collection of vectors u1 through un such that the set of these vectors, so ui, where I goes from 1 to n, is orthonormal. Right? And if you remember, a set of vectors is orthonormal if it's orthogonal and the magnitude of every vector is 1, right? So let's prove this. Well, what do we start with, right? We start with our assumption, and our assumption is that we have a real symmetric matrix A, right? So A, real symmetric, implies, well, by the theorem in the last video, we have that there it is, that the eigenvalues are necessarily real, right? And so what this means is that the diagonal matrix D, the elements are equal to their conjugate, right? In the complex setting, a number is equal to its conjugate if and only if it's a real number, right? We also know there exists this diagonal matrix D such that D is equal to U transpose A U. What does this mean, right? Well, also we have, I'll just say it now, D is equal to, lambda 1 through lambda n, because that will come into play here soon. If we have D is equal to U transpose A U, well then, if U is orthogonal, then U transpose is equal to the inverse. And so this is equal to U inverse A U. We can multiply on the left by the orthogonal matrix U to both sides. And what we would get is UD equals AU, right? And so let's unpack this equality and see what we can learn here, right? Because what are we trying to do? We're trying to find a collection of vectors that is orthonormal. So let's say U is, well, let's say U is the orthogonal matrix where each column is this U1 through UN here. And I got ahead of myself here, such that UI is an eigenvector for all I, right? That's a pretty important detail I left out. You probably shouldn't listen to me. So what this corollary is saying is that if you have a real symmetric matrix, you can find a set of eigenvectors that is an orthonormal set, right? And so our orthogonal matrix here, U, is composed of the eigenvectors. Why do we do that? If you remember when we were talking about diagonalizing a matrix, we can diagonalize a matrix if and only if the invertible matrix P was the augmentation of all the eigenvectors of A, right? Well, in here, having this criteria is the same as, or it implies that A is similar to D. So that means we can write U as this matrix U1 through UN. So what does this mean? Well, let's start with understanding the product AU. This is A times U1, U2, blah, 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 through UN. What is this product, right? Well, what you would do is you would take, when you take the product, you would take the first column vector of U, right? Take the dot product of every row vector in A. What that would turn into is AU1, AU2, blah, 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 AUN. Okay, but what do we have here? We have that U1 through UN are eigenvectors. And so because of that, we know that right? What's the criteria to be an eigenvector? It's that AX equals lambda X. So let's replace AU1, blah, 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 with the corresponding products or scale based on the eigenvalue, right? So here we would have A lambda 1, or it's more natural to write lambda 1, A, blah, 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 lambda n, A, right? Excuse me. Lambda 1, U1, et cetera, lambda n, UN, right? But what is this equal to? Remember, the diagonal matrix D is the matrix with entries along the diagonal that consist of the eigenvalues. So this is equal to D times U, right? Or UD. So what does this mean? Well, this means that AUI is equal to lambda I UI for all I. And moreover, we have that since, what else do we have here? We have that UI, this collection, these are the eigenvectors of A. And our conclusion is since U is orthogonal, what does that mean? Well, that means the I, jth entry of UT times U, well, since we know that's the identity, that's what it means to be orthogonal, well, this means the ijth entry of UTU is equal, so this is equal to the Kronecker delta symbol, delta ij, and if you remember, this is a function that's 0 when I is not j, and it's 1 when I is equal to j, right? What does this mean? Well, when you take the dot product, if we have that ui j, right? We have that ui dot uj is the Kronecker delta symbol. Well, then we have that this is 0 for all ij such that I is not equal to j. This implies that the collection of vectors, of eigenvectors ui, I goes from 1 to n, is an orthonormal set. Okay, so what we can do now is for any given matrix that's real and symmetric, we can find an orthonormal collection of eigenvectors, right? And this, I don't think we'll be able to cover it in the time that's left, but having an orthonormal collection of eigenvectors, the application of looking at the spanning set or this set as a basis for some space, this has a lot of implications in quantum mechanics, which is very interesting. Okay, so let's do an example. Let's say we want to find an orthonormal set of eigenvectors for A, which is the matrix 17, -2, -2, -2, -2, 6, 6, 4, 4. Right? And you can tell this is symmetric. So what does this mean? Well, this means we expect that the eigenvalues are real, right? And distinct. So, well, and also that the eigenvectors are orthogonal, but we'll get to that first. I'll leave this as an exercise since we've done plenty of examples of computing eigenvalues now. You get, well, let's show that lambda 1, the eigenvalues you get are 18, 9, and 2, with the corresponding eigenvectors. X1 is -4, 1, 1. X2 is, well, it's not the eigenvector, it's an eigenvector, right? Because you always get an infinite family of eigenvectors. And then we also get x3 is 0, -1, 1. So this is a good exercise, especially as we approach the final. As much as we've talked about eigenvalues and eigenvectors, you can absolutely expect an eigenproblem. So if we know by theorem, we know that the set x1, x2, x3 is an orthogonal set, then how do we get an orthonormal set? Well, we take the orthogonal set and we scale each vector by 1 over its magnitude, right? And then if you do this, you get 1 over root 18 times x1, 1/3 times x2, and 1 over root 2 times x3. And you can see if you take the dot product of any pair of these vectors, you get 0. If you take the dot product of any of these vectors with itself, you get 1. All right. So throughout what we've covered, it's been very apparent that there is a lot of analogous properties between symmetric matrices and diagonalizable matrices, right? So I pose the following claim, and that is that if A is symmetric, that implies that A is diagonalizable. Well, let's prove this. If we have that A is real and symmetric, so sorry, say real, by a previous theorem, that implies there exists an orthogonal matrix U such that we have U transpose A U is equal to a diagonal matrix D. Well, when U is orthogonal, that implies that the transpose of U is the same as the inverse. So this implies that U inverse A U equals D, which implies that A is similar to D, right? And if A is similar to D, that means A is diagonalizable. Cool. Now that we know symmetric implies diagonalizability, we can state the following theorem, is that if A is diagonalizable, this condition is equivalent to the set, we'll say x1 through xn of eigenvectors of A is orthonormal. That's bad handwriting. Orthonormal, right? And so this is an if and only if. And so another way that we can see if a matrix is diagonalizable is to see if the set of eigenvectors is orthonormal. Okay, I have another theorem relevant to spectral theory of orthogonal matrices. Let's say if A has n real eigenvalues, i.e. lambda I is an element of R for all I ranging from 1 to n, then there exists an orthogonal matrix U such that U transpose AU is upper triangular. Right? Remember when we were studying LU factorization, we were writing matrices as the product of a lower triangular matrix and an upper triangular matrix. So we have this result, and then we also have a corollary based on this result. We have, if A has eigenvalues, say lambda 1 through lambda n, then the determinant of A is equal to the product of the eigenvalues, right? And this makes sense because if A, again, this is real symmetric here. If A is symmetric, that implies it's diagonalizable, which implies, right, if A is symmetric to a diagonal matrix, that means they have the same eigenvalues. And so the determinant of A is just the product of the entries along the diagonal, which we know are the eigenvalues. So this is a product of lambda I, right? If you've never seen this capital pi here, this is lambda 1 times lambda 2 times blah, 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 times lambda n. We also have that the trace of A is equal to the sum of the eigenvalues, right? I goes from 1 to n, lambda I, which we know this all too well from the nightmare that is Calc 2, plus blah, 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 plus lambda n. Okay. So using spectral theory, we can also calculate a determinant and a trace much easier for an arbitrarily complicated matrix, right? Well, we know how to compute the eigenvalues, and if the matrix is really that nasty, then that's less work than trying to compute a determinant. And so if we have a real symmetric matrix, then computing the determinant and the trace become a much easier task.